Good morning to one and all. Today in this live lecture, we shall study the proof of Heaviside's theorem and complex inversion theorem or complex inversion formula for inverse Laplace transformation. Also, we have discussed the problems based on this, that is problems based on the Heaviside's theorem, problems based on the complex inversion theorem. Now, we have to discuss here, 1 minute. आवाज येतो का रे? तर ठीक आहे. Now we shall discuss this complex inversion theorem. Now, what is the complex inversion theorem? Which is the proof of the complex inversion theorem? Now we have to discuss here. Okay, now Heaviside theorem and complex inversion formula. Actually, this is the lecture number 15. This is the last but one lecture for the first unit. Now we have to discuss the Heaviside's theorem and complex inversion formula. Okay. Now see this. Actually, this is the last but one part of our syllabus. Here. Actually, this is the definition of the Laplace transform. If the kernel K, S comma T, is defined as K of S comma T, which is equals to 0 for T is less than 0, and which is equals to e raised to minus st for T is greater than 0, then the resulting transform, capital S f of S, which is equals to integral from 0 to infinity e raised to minus st into f of t dt. See this, or we can write L of small f of t, which is equals to capital F of p, which is equals to integral from 0 to infinity e raised to minus pt into f of t dt. Number of times which we have studied this formula and number of different types of problems which we have solved in this chapter. Now we shall move towards, actually this is the definition of the inverse Laplace transform. See this, if the Laplace transform of small f of t is capital F of p, then small f of t is called as inverse Laplace transform of capital F of p. That means L of small f of t is equals to capital F of p, then we can write L inverse of capital F of p, which is equals to small f of t. Here the notation L inverse is called inverse transformation operation, Laplace inverse. These are the basic definitions which we have studied already. Proof of already these definitions, basic formulae which we have studied. The Laplace transform of some typical functions. So these are the formulae based on the Laplace transformation, and on that side, that are the formulae of inverse Laplace transform. If L of 1 is equals to 1 upon p, Laplace transform of 1 is 1 upon p, then its inverse, L inverse of 1 upon p is 1. So we have written here comparatively formulae for Laplace transform and inverse Laplace transform. See this, you must know. Okay, these are also formulae based on the Laplace transform. These are the properties regarding the inverse Laplace transform as like Laplace transform. These are different properties of the inverse Laplace transform. Okay, these are some basic theorems based on the Laplace transform. Already we have studied the problems based on the inverse Laplace transform by using partial fraction method. So these are the different partial fraction methods which we have to use for the solution of the problem. Now actually the basic idea or the basic concept of Heaviside's theorem, theorems on inverse Laplace transform. In that theorems, first Heaviside expansion theorem. Actually, Heaviside expansion theorem, which is based on the partial fraction. We have to find out the L inverse of capital F of P divided by capital G of P. L inverse of capital F of P divided by capital G of P. Then we have to solve this inverse of this fraction, rational algebraic expression, whose degree of denominator is less than the degree of numerator must be less than the degree of denominator. Then we can use the partial fraction, or we have to use the Heaviside's theorem here. So the statement of the Heaviside theorem, student, you must know the statement of Heaviside theorem. Which is the statement of Heaviside theorems here? 1 minute. Now see this. Now see here. Statement of the Heaviside theorem here. See this. Let capital F of P and capital G of P be the two polynomials in P, where capital F of P has a degree less than that of a capital G of P. If capital G of P has n distinct zeros, alpha r is equals to 1, 2, 3 dot 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 n. That is, we can express capital G of P in the factor form. P minus alpha 1 into P minus alpha 2 into P minus alpha 3 dot 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 P minus alpha n. Then we have to prove that L inverse of capital F of G, capital F of P divided by capital F of G, which is equals to summation r is equals to 1 to n F of alpha r divided by G dash of alpha r into e raised to alpha r into t. We have to prove this result. Okay. 1 minute, student. One minute. See this. We have to write this. Okay. Now we have to prove this result. Given that, proof. Given that capital G of P has a distinct zeros, n distinct zeros alpha r, where r is equals to 1, 2, 3 dot 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 n. So we can write capital F of P divided by capital G of P, which is equals to capital F of P divided by, we can write this capital G of P in the form of a factor. See this. Capital G of P, we can write P minus alpha 1, P minus alpha 2. These are the factors of the capital G of P. So we have to write in place of capital G of P, P minus alpha 1 into P minus alpha 2 dot 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 P minus alpha n. So we can write this partial fraction form. Denominator is in the linear product form. So we can write first linear term a divided by a1 divided by P minus alpha 1 in the partial fraction form. This rational algebraic expression we can write in the partial fraction form, a1 divided by P minus alpha 1 plus a2 divided by P minus alpha 2 plus dot 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 plus ar divided by P minus alpha r plus dot 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 plus an divided by P minus alpha n. So general term, see this ar is the general term, alpha is the general term. So where a1, a2, a3 dot 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 ar dot 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 an be the partial fraction constants, be the partial fraction constant to be determined by multiplying P minus alpha and taking the limit as a P tends to alpha, we get. See this. As like this method of a partial fractions, here there are two linear terms, 1 upon x minus a into x minus b. Then we know that how to take the partial fraction of this term, a divided by x minus a plus b divided by x minus b. Here capital A and capital B are called partial fractions constant, and which is to be determined by putting some particular values. This is the second type of a partial fraction which has three linear terms in the denominator. So we can take the partial fraction in this way. So here in this case, capital F of p divided by p minus alpha 1 into p minus alpha 2 into p minus dot dot dot. So its partial fraction we can take by taking, there are n number of brackets, linear terms bracket. So we need n constant, capital A1, capital A2, capital A3 dot 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 capital A n, and these are the constant which are used for the partial fraction and which are determined by the multiplying p minus alpha and taking the limit as a p tends to alpha. Actually this is very important theorem and simple theorem. So we can find the value of AR. AR means A1, A2, A3, capital A1, capital A2 in this way. So we can find the value of capital AR is equals to limit p tends to alpha, capital F of p divided by capital G of p into p minus alpha. If we put this limit, then what will happen here, students? What will happen here? One minute. Students, take a minute. Now we shall see this. Capital AR is equals to limit p tends to alpha, capital F of p into capital G of p, p minus alpha. If we put direct p tends to alpha, then we will get 0 and we will get the form 0 by 0 form. 0 by 0 form. And for the 0 by 0 form, we know that there is a one method to obtain the limit, and that method is called as a L-Hospital rule. So here in this case, 0 by 0 form, to find the limit of this function, we have to use L-Hospital rule. L-Hospital rule means we have to take the derivative. You have to take the derivative. How we can take the derivatives here? Derivative of numerator separately and derivative of denominator separately. In the numerator, there are two terms. Which are those? Capital F of p into p minus alpha. And in the denominator, there is a capital G of p. So, what is the L-Hospital rule? If limit x tends to a, capital F of x divided by small f of x, which is of the form 0 by 0, then that limit is equivalent to limit x tends to a, capital F dash of x divided by small f dash of x. This method is called as a L-Hospital rule, L-Hospital method. So here we have to use L-Hospital rule. So we have to take the separate derivative of numerator and separate derivative of denominator. So in the numerator there are two terms. In the numerator there are two terms. This is in the numerator. So there are two terms. So we have to find out its derivative. We have to find out its derivative by using the product rule. Product rule. In the numerator, L-Hospital rule is used in such a way that we can't take derivative by using the formula division rule, because in the L-Hospital rule we have to take separate derivative of numerator and separate derivative of denominator. So first of all we have to take the derivative of numerator separately. In the numerator there are two terms, capital F of p and p minus alpha. So we have to take the product rule. So second is it is P minus alpha r, derivative of first capital F dash of P, plus again first is it is capital F dash of P into derivative of second, into derivative of second means P minus alpha r चा derivative येतो 1. So this is the L'Hospital rule we have to use here. 1 minute. So this is the derivative of numerator. In the denominator there is only one term, that term is capital G of P, so its derivative is G dash of P. So its derivative is G dash of P. So now if we apply the limit now, for in this step if we apply the limit alpha P tends to alpha, means here P tends to alpha, alpha minus alpha means 0, 0 into capital F dash of P means 0, that goes to 0, plus capital F of P divided by G dash of P. So capital AR is equals to, we will get the result capital F of alpha R divided by G dash of alpha R. That means in place of P we have to write alpha R here. In the place of P we have to write alpha R here. So we have to write alpha R in the both. Here we have to write alpha R. Again here we have to write alpha R, and this term goes to 0. This term goes to 0. So we will get AR is equals to capital F of alpha R divided by G dash of alpha R. From equation 1 we get, now from equation 1 we can write this A1, A2. How we can write from this? This is the general term AR. So we can write A1. A1 means capital F of alpha 1 divided by G dash of alpha 1. We have to put the value of A2, capital alpha F of alpha 2 divided by capital G dash of alpha 2. We have to put value of AN, F of alpha n divided by G dash of alpha n. Putting these values A1, A2, A3, AR, AN in equation 1. In equation 1. So we will get capital F of P divided by capital G of P. In place of A1, we have to write capital F of alpha 1 divided by capital G dash of alpha 1 into denominator, keep this as it is, 1 upon P minus alpha, plus in place of A2 we have to put capital F of alpha 2 divided by capital G dash of alpha 2 into keep 1 upon P minus alpha 2. In place of AR you have to put what we have to put in place of AR, student? Now you tell me, who are attending these lectures online, now you tell me which value we have to put in place of AR. So we have to put the value of AR according to our calculation, capital F of alpha divided by G dash of alpha into keep this 1 upon P minus alpha. In this way, in this equation we can get the result as capital F of P divided by capital G of P is equals to, in this way, by putting A1, A2, A3 in equation 1. So again now we have to take inverse Laplace transform. Actually we have to calculate, here see this, we have to calculate L inverse of capital F of P divided by capital G of P. So this is the expansion, capital F of P divided by capital G of P we can write in the form of summation form, or we can say that the partial fraction form. This is the partial fraction. Now we have to take the inverse Laplace transform of this on both sides. So by taking inverse Laplace transform on both sides, so on the left side there is a notation L inverse of capital F of P divided by capital G of P. Put this capital F of alpha 1 divided by capital G dash of alpha 1, keep this as it is. Then we have to take L inverse of 1 upon P minus alpha 1. and there is one formula. See this, L inverse of 1 upon, see this, L inverse of, according to the second formula, L inverse of 1 upon P minus A, we can write e raised to a t. So here we have to write 1 upon P minus alpha 1 is e raised to alpha 1 into t. So we will get capital F of alpha 1 divided by g dash of alpha 1 e raised to alpha 1 t. Similarly, second term, capital F of alpha 2 divided by g dash of alpha 2 e raised to alpha 2 dot 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 in this way, and we can write these terms in the summation form. R is equals to 1 to n, summation R is equals to, summation from R is equals to 1 to n, capital F of alpha r divided by g dash of alpha r into e raised to alpha r t. And this is our required proof. Student, do you understand this theorem? Students, have you understand? Do you understand this theorem? Okay, so we can get the Heaviside's expansion formula. This is the Heaviside's expansion formula. Actually, the basic idea of this Heaviside's expansion formula is the partial fraction. This is the simple concept you must know. The basic idea is based on Heaviside's expansion theorem is totally based on the partial formula, partial fraction. Okay. Do you understand? If you have any doubt in any step, then you can ask me. I will give you a particular answer, particular explanation for that step. Actually, this is very important theorem, and this is a very simple theorem. Okay. Only here turning step is you have to use L'Hospital rule. L'Hospital rule means limit, if the given fraction is in the form 0 by 0 or infinity by infinity, then its limit we can obtain by taking derivative of numerator separately, derivative of denominator separately. This method is called as a L'Hospital method, L'Hospital rule. So here we have to calculate the L'Hospital rule, and after putting the limit we will get the value of AR. So we can get A1, A2, A3, A4 dot 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 in this way. Okay. So this is the Heaviside's expansion formula. Now this is the see this is the assignment number 14. You can calculate the problems based on this. हे तुम्ही प्रॉब्लेम सॉल्व करू शकता. अगोदर घेतलेले आहेत त्या पद्धतीने तुम्ही हे प्रॉब्लेम सॉल्व करा. ठीक आहे. Now next we shall move towards the second theorem, complex inversion theorem for the Laplace transform, or complex inversion formula for the Laplace transform. This is also one important theorem. You must know the proof of this theorem also. The statement of this complex inversion theorem is, if capital F of P is an analytic function, capital F of P is an analytic function of the complex variable P in the half plane real part of P which is greater than C, and further if F of t has a continuous derivative and is of exponential order such that L of small f of t is equals to capital F of P, or L inverse of capital F of P is equals to small f of t, then we have to prove F of t is equals to 1 upon 2 pi I integral from C plus I alpha, I means here iota, C plus iota alpha to C minus iota alpha, imaginary unit number. Okay, so we can, in the simple way, we can say I, C plus I alpha, C plus I infinity to C minus I infinity e raised to pt into capital F of P dP. This value is for x greater than 0, sorry, t greater than 0. This value is for 1 minute. This value is for t greater than 0. Here is t. And value of this f of t is 0 if t is less than 0. This is t. Student, this is a t. T greater than 0, t less than 0. You must know. Okay? तर okay, we shall discuss. Okay, very good. Actually, this is a very nice example. Here we said step function. This is a different type of function, which is the step function, which has a particular values. You know, there are different steps functions. Such a way, there is another function, Heaviside step function. There is no any relation between Heaviside's expansion theorem and Heaviside's step function. That concept is a different. Okay, we shall discuss that on later on. So f of t is equals to 1 upon 2 pi into I, integral from c plus iota infinity to c minus iota infinity e raised to pt into capital F of p dp when t is greater than 0. And the corresponding value for f of t, another value is 0 when t is less than or equals to 0. Now we have to prove this. We have to prove this result. If t is less than 0, then we can say it is a 0. Now for t greater than 0, it is very important. For t greater than 0, we have to prove this theorem. Okay? Now discuss this. Actually, we know that according to the definition of the Laplace transform, see this, according to the definition of the Laplace transform, capital F of p is equals to integral from 0 to infinity e raised to minus pt into f of t dt. This is a basic formula, but we have written this formula in the form of u because already we have to prove this function in the form of t. We have to prove this theorem in the form of t. So we have taken here definition of the Laplace transform in the form of u. So we have considered in the form of u. We have to consider this integration. According to the Laplace transformation, we have considered the variable of this integral is in the form of u. We can write in the form of t, but here in this case already we have given the function in the form of t. So to differentiate or to separate, to show the separate functions, we have considered here the function in the form of u. So according to the definition of the Laplace transform, you know that capital F of p, 1 minute, capital F of p, which is equals to integral from 0 to infinity e raised to minus pu into f of u du. Now actually we know that this is a convergence absolutely, and according to the definition, and uniformly in the half plane, real part of p is greater than c2, which is greater than or equals to c2, which is greater than c0, because according to the given statement it is the exponential order function. F of t is exponential order function and which is a continuous derivative. So according to that condition, given condition, we can write this. According to the definition of the exponential order, we can write this. Also, capital F of p is analytic in the half plane. Real part of p is greater than c or c naught. So this is analytic function. In the statement we have given capital F of p is analytic function. So we can write capital F of p is analytic in the half plane real part of p. Now see here student, actually we have to show that capital F of t, f of t is equals to 1 upon 2 pi iota integral from c plus I infinity to c minus I infinity e raised to pt into capital F of p dp. So first of all we have to consider this term only. On the right side, we have to consider the integral of this. And by taking the solution of integral, we have to show that the integral value of this integral is 2 pi I into f of t. This is our aim. This is our method of proof. What we have to show? We have to show that the value of this integral from c plus I alpha to c minus I alpha e raised to pt f of f of p into dp, we have to show that its value is 2 pi I into f of t, which completes the proof. Okay, so here we have considered the integral part, integration. So we have taken here this integral in the form of a lambda. Lambda tends to suppose infinity. So we have considered c minus iota lambda to c plus I lambda e raised to pt capital F of p into dp. Okay, which is equals to, we can write this. See here, we have considered the integral part on right side and lambda tends to suppose infinity. So this will be c minus I infinity to c plus I infinity. Now we have to solve this. Now replace this capital F of p by using this equation. Suppose 1. Capital F of p means integral from 0 to infinity e raised to minus pu into f of u du. So replace this integral part in here in place of capital F of p. See this. In place of capital F of p, we have replaced according to the definition of the Laplace transform. So our integral becomes c minus integral on right side c minus I lambda to c plus I lambda e raised to pt, again into integral from 0 to infinity e raised to minus pu into f of u du into dp. So here on the right side there are double integral. First integral is with respect to p and second integral from 0 to infinity with respect to u, due to the introduction of capital F of p. So now by rearrangement of this, by rearrangement of these integrals, we will get, by rearrangement of this integral, we can write, keep this integral 0 to infinity. Keep this 0 to infinity, f of u du as it is. Now we have to solve inner integral, second integral in the form of t, in the form of p, so dp. So integral from c minus I lambda to c plus I lambda e raised to, now see here, e raised to pt into e raised to minus pu. By the rule of indices, base in the product base is the same, so we can write addition of the numerator. So e raised to p2 into e raised to minus pu, we can write e raised to p into t minus u dp. Do you understand this? अरे इथं स्टेप समजली का तुम्हाला? Do you understand? We have to rearrange these two integrals. Keep this first integral with respect to u as it is 0 to infinity. We have to solve integration with respect to p. And so here there is a product e raised to pt into e raised to minus pu. We can write e raised to p into t minus u. Now our aim is to find out this integral. Integration with respect to p. Keep this integration with respect to u as it is because this is a double integral. So calculate this integration with respect to p. So you know that what is the integration of e raised to at with respect to t? Integration of e raised to at with respect to t is e raised to at divided by a. So we can write this integral, calculate this integral with respect to p. See here. Then we can write e raised to integration of e raised to p into t minus u dp. We will get the result as e raised to p into t minus u divided by t minus u. This is the integration of e raised to p into t minus u with respect to p. Keep this du as it is and its limits. Lower limit is c minus I lambda to upper limit is c plus I lambda. Okay, so keep this limit c minus I lambda to c plus I lambda. I means here iota. Okay, imaginary unit number. Okay, so e raised to I into t minus u divided by t minus u du. Again, keep the upper limit and lower limit. If we put the upper limit in place of p, because this is an integration with respect to p which we have solved, so keep this upper limit in place of p, c plus I lambda t minus u as it is, minus, keep this lower limit in place of p, c minus I lambda into t minus u. Do you understand this? Upper limit and lower limit. If we put upper limit and lower limit, keep this du as it is. Keep this du as it is. So, 1 minute. So du is as it is. Now here we can calculate this. Again, see this e raised to c into t minus u. E raised to c into t minus u. Here c into t minus u. Here e raised to c into t minus u. You can take a common. So we will get c raised to t minus u. See this. This is the c raised to t minus u common term. Then which are the remaining term? In the bracket there is e raised to I lambda into t minus u minus e raised to minus I lambda into t minus u. So we will get integration with respect to u. Remaining terms are same. Integral from 0 to infinity f of u e raised to c into t minus u. So we will get this function as e raised to I lambda into t minus u minus e raised to I lambda into t minus u divided by t minus u. Again we have to use the formula for this. You know that. Who can tell me? Student, who can tell me what is the formula for e raised to I theta? Now tell me, what is the formula for e raised to I theta? Again same, we have to use e raised to minus I theta. E raised to minus I theta. Who can tell me? Actually in the imaginary number there is a separate formula which we have to use in the trigonometric form. E raised to I theta we can write in the trigonometric form. Who can tell me what is the formula for e raised to I theta? We can write in the form of a trigonometric expansion or trigonometric formula. So, tell me student. सांगताय का कुणी? E raised to I theta. What is the formula for the e raised to I theta in the trigonometric form? So, I shall write here. Actually, the basic formula regarding e raised to I theta is cos theta plus I sin theta. E raised to minus I theta means cos theta minus I sin theta. So, we know that the addition e raised to I theta plus e raised to minus I theta we can write by adding these two terms, first and second equation, we will get 2 cos theta. So, e raised to I theta minus e raised to minus I theta, we will get 2I sin theta. In this way, according to the last formula, e raised to I theta minus e raised to minus I theta into 2I sin theta. We can use this formula here. E raised to I lambda t minus u minus e raised to minus I lambda t minus u means e raised to I theta minus e raised to minus I theta. Then we will get 2I sin theta. So in this way, we can write here 2I sin lambda into t minus u divided by t minus u. Do you understand? समजलं का रे स्टूडेंट हे? समजतंय का? So we will write this as 2I sin lambda t minus u to t minus u and keep this e raised to t c into t minus u as it is. Okay. Now 2I is the constant term, I is the iota. We can take out of integral. So we will get 2I integral from 0 to infinity f of u into e raised to c into t minus u into sin lambda t minus u divided by t minus u du. Now we have to substitute. We have to change the limit. we have to change the limit of this integral, or we have to substitute the variable. That means put u is equals to t plus x, or we can write here t. So du is equals to dx. We have to change the variable. In place of t minus u, we have to replace. We have to change in the form of plus. So keep this variable u. We have to change this u in the form of t plus x. So student, consider, put u is equals to t plus x. So by differentiating, du is equals to dx. Du is equals to dx. U is a variable. In this integration, u is a variable. We have to convert that variable in the form of x. So x is another variable. So du is equals to dx. Now when we substitute the variable in the definite integral, then corresponding limits also we have to take. When the lower limit is for u is equals to 0, if we put u is equals to 0, then lower limit will be x is equals to minus t. Upper limit is for u is equals to infinity. When we put u is equals to infinity in our substitution, then we will get x is equals to t minus infinity. Infinity minus t. Infinity minus t means again infinity. So we have to write new limits, that is minus t to infinity in the given integral. Keep left side as it is. On the right side, 2I integral from minus t to infinity. In place of u, see this, 1 minute. In place of u, we have to put t plus x. In place of u, we have to put t plus x. Plus t minus t will be get cancelled. So it will be c into e raised to ct here. Okay. So we can write this as, in place of u, you have to write t minus inner bracket t plus u. So we will get these two terms. If we put in place of u, then we will get these two terms. Okay. And in place of t minus u, which is equals to x, minus x, divide sine of lambda minus x divided by minus x, that will be sine lambda x divided by x. That means students, see this, according to our substitution, the new form of integral will becomes in this way. Now e raised to ct is a constant term, so we can take out of integration. So this is a new integral. So our integral becomes, 1 minute. So our integral becomes 2I e raised to ct into integral from minus t to infinity f of t plus x into e raised to minus c into t plus x into sine lambda x divided by x dx. And here we have to use one lemma which we have studied in the complex analysis. That lemma is, I am written here. What is that lemma? If lambda tends to infinity, 1 upon pi minus infinity to plus infinity. But here integration is minus t to infinity. There is no problem. F of x plus t into sine lambda t divided by t dt, which is equals to f of x. This is the lemma which we have studied in the complex analysis. Here we have to use this lemma here and keep this pi here. So integral from minus pi to plus pi here. So we have to use this integral from minus t to infinity f of t plus x into sine lambda x divided by x, which can be written as, see this, pi into f of t. Keep this 2i as it is, e raised to ct as it is, and when this is a x greater than 0, t greater than 0, so we can write here x is a 0, so e raised to ct. Here we have to write e raised to ct. So according to that lemma, we can write pi into f of t. Remaining terms are as it is, and x tends to 0 here. So we will get the result as, 1 minute, I have reduced this. Okay. So our, due to this lemma, the value of integral becomes e raised pi into f of t. Pi into f of t. Keep this to I as it is, e raised to ct as it is, e raised to minus c into t, x 0. So we will get this as e raised to minus ct. So in this way, we can write as 2 pi I into f of t. Now transfer this 2 pi I on f of t on the left side. So we will get the final result with this integral. F of t is equals to 1 upon 2 pi I integral from c minus I lambda to c plus I lambda e raised to pt capital F of p dp. But we have considered lambda tends to infinity. So our final result will be small f of t is equals to 1 upon 2 pi iota c minus I infinity to c plus I infinity e raised to pt into capital F of p dp, and hence proved. In this way we can prove the complex inversion theorem. See this complex inversion theorem or Brownish integral formula. This is also known as a Brownish integral formula. Here total theorem which we have proved in the form of lambda. See this. We have replaced infinity in place of infinity lambda because we have considered lambda tends to infinity. Okay. So in this way, this is the proof of this theorem. If you have any doubt, then you can ask. Okay. Here is an important lemma we have to use here, student. You have to use, 1 minute. We have to use important theorem. That theorem is important lemma which we have studied in the complex analysis. If f is integrable on entire real axis and x is a point which is a continuity of f, then lambda tends to infinity 1 upon pi, which is equals to f dash of f of x. Okay. So this completes the proof. If you have any doubt, then you can ask me in the lecture also. Now see this one example which we have to study here, which is based on the complex inversion formula. Show that L of e raised to ax minus 1 divided by a, which is equals to 1 upon p into p minus a. Also by using the complex inversion formula, prove that L inverse of 1 upon p into p minus a, which is equals to e raised to ax minus 1 divided by a. Now this is a simple problem. F of x is equals to e raised to ax minus 1 divided by a. So by taking the Laplace transform, 1 minute. By taking the Laplace transform, L of e raised to x minus 1 divided by a. A is the constant, so you can keep as it is, 1 upon a. L of e raised to ax minus L of 1. L of e raised to x is 1 upon p minus a according to the definition, minus 1 upon L of 1 means 1 upon p. By taking LCM, we will get the result 1 upon p into p minus a. This is the first part of this example, and this is very simple example. हा सिंपल एक्झाम्पल आहे, यात काय अडचण नाही आहे. त्यानंतर आता actually we suppose that, so we will get the result L of e raised to x minus 1 divided by a is equals to 1 upon p into p minus a, which is equals to capital F of p. Now by the complex inversion theorem, f of x is equals to 1 upon 2 pi I integral from c minus I lambda to c plus I lambda e raised to px into capital F of p dp. In place of lambda, you can use infinity also. Now, so here replace this value, capital F of P means what? See here. See here, capital F of P means capital F of P means you have to use 1 minute. Capital F of P means 1 upon P minus 1. So we have P into P minus A. We have to replace it here into dP. This is a dP. So f of x is equals to 1 upon 2 pi I integral from c minus I lambda to c plus I lambda e raised to px into 1 upon p into p minus a dp. Now there is one theorem or basic idea which we have studied in the complex analysis. The summation residues of e raised to px divided by p into p minus a at the simple pole, which are poles p is equals to 0 and p is equals to a. These are the poles of this. So at the simple poles we can write limit p tends to 0, p into e raised to px divided by p into p minus a plus limit p tends to a, p minus a into e raised to px divided by p into p minus a. This is which we have studied in the complex analysis, summation of residue. So by taking p tends to 0, limit of this first fraction p tends to 0, p will be get cancelled, e raised to px divided by p minus a, as a p tends to 0, e raised to 0 divided by 0 minus a, so we will get 1 upon minus a. In the second p minus a will be get cancelled, as a p tends to a we will get e raised to ax divided by a in place of p tends to a, if we put p tends to a. So 1 upon minus a plus e raised to x divided by a, so we will get this result. So f of x is equals to e raised to a minus 1 divided by a. Hence L inverse of capital F of P, which is equals to f of x is equals to e raised to x minus 1 divided by a. This is the complex example of based on the complex inversion theorem. Example based on complex inversion theorem. We have to use here complex inversion formula, and by using this complex analysis concept we can find the solution in this way. Okay, समझ लगा? If you have any doubt, then you can ask me in the class also, or in the chat box you can write your any difficulty, then I will solve it. Now again there is another lecture we shall take at 8 p.m. at the 8 p.m. which is the last lecture. Some initial value theorem and final value theorem which we have to take in the evening lecture. So we shall stop here. If you have any doubt, then you can ask me. Okay. संध्याकाळी परत एकदा आपलं